Okay, we'll be going to our next talk. And the topic is diagnostic of the cause of Robert Williams failure in the paint shop company Marielli. You have which of it? I'm lost when I have to speak Serbian. I'm just relative as a person. So, I apologize, I read the wrong line. So you will give me a lower mark this time. So I'm sorry. So it is effect of increased trend of fracture toughness using non-standard PCVN specimens and implications for the reference temperature. I apologize. I tried to convince you to use the other topic.
Good afternoon, everyone. My name is Vitor. I am a PhD student at University of São Paulo, and Professor Claudio Ruggieri is my advisor. Today, I would like to talk about the effects of increased span on fracture toughness using non-standard pre-cracked sharp EV0 specimens and the implications for the reference temperature. Firstly, I'm going to talk about fracture toughness tests, constraint effects, and the estimation procedure in non-band geometries. And after, I will show an application in fracture testing of a typical structural steel and a T0 evaluation of the reference temperature. Finally, conclusions and next steps. The PCVN specimens are extensively used to evaluate fracture toughness in several engineering structures, but there is some questions about these specimens, as I will comment in the next slides. In the context of integrity assessments of reactor pressure vessels, it is known that RPV steels become progressively brittle during service life due to neutral irradiation. So the assessment of material degradation is essential to guarantee RPV structural integrity. One of the most rational procedures to evaluate material degradation is based on master curve methodology, which provides a reference temperature and correlates the median fracture toughness with the temperature in the ductile to brittle transition region. And the standard test method for determination of the reference temperature has some key features, such as high constraint specimens, the KJC values are obtained from J values, and among other features, as we can see in this picture. And in some cases, the use of sub-size specimens becomes increasingly necessary due to severe limitations on the material availability. While extensively used in surveillance programs to assess nuclear irradiation embrittlement, pre-cracked sharp specimens under bending load exhibit significant plasticity and constraint loss, which can result in a possible breakdown of mechanical similitude. Research shows that specimen dimension has potential influence on T0. For example, PCVN specimen tends to show a smaller T0 than 1T standard specimen. And this picture, we can see more detail this influence. As you can see, as the specimen dimension decreases, the reference temperature also decreases by this trend line. Motivated by these observations, this study evaluates the applicability and feasibility of non-standard band geometries in mitigating the often observed effects of constraint loss on fracture toughness values of sub-sized specimens. Here we have analysis matrix of fracture toughness tests. And we have done fracture toughness tests in PCVN geometries with different S/W ratios. And in order to assess the potential influence of side grooves on fracture toughness values, fracture tests were also conducted on pre-cracked sharp EV0 specimens with S/W equals to 6. And for numerical analysis, it was employed the typical finite element model constructed for plane strain analysis. And in order to assess the potential influence of increased span on crack tip constraint, the JQ methodology is employed, where Q parameter defines the level of crack tip constraint. And here we have some results of constraint effects of 3-point band tests with different S over W ratios. And here, as you can see, for example, for a moderate strain hardening behavior, as the increased span increase, the crack tip constraint also increases. And the same behavior can be observed for a high strain hardening behavior and for a low strain hardening behavior. Before analyzing the fracture toughness values obtained from non-standard specimens, it should be noted that the current procedure to evaluate the values is based only on standard 3-point band geometry with S over W equals to 4. So we provide a new set of eta factor to evaluate J values obtained from non-standard band geometries. The J estimation procedure is based on load and displacement curve by eta methodology. The eta factor simply relates the plastic contribution to the strain energy, and in this case the plastic work is defined as the area under load and displacement curve. Here we have the results of eta factors for 3-point band geometries with different S over W ratios for different strain hardening behavior. Firstly, it can be observed that the eta values obtained from standard 3-point band geometry, the eta values are very similar to the eta values provided by ASTM E1820. And here we can also observe that as the S over W ratio increases, the eta values also increase. And it can be observed that for a same S over W ratio, the eta values exhibit very little sensitivity for different strain hardening behavior. After the foregoing procedure, it's possible to evaluate J values obtained from non-standard band geometries. The material employed in this study is a typical high-strength low alloy steel with low carbon content and niobium vanadium in its composition. The microstructure of this steel is composed of ferrite and perlite, and the mechanical properties were evaluated at both room and low temperature. Here it can be observed that this steel exhibits a moderate strain hardening behavior at both temperatures. This is the sharp impact energy curve, and the fracture toughness test temperature was defined at minus 20 degrees, which is near to ductile to brittle transition region. And the master curve methodology employs a 3-parameter variable distribution to describe the scatter in fracture toughness data. And this distribution provides a characteristic toughness which will be used to determine the reference temperature. And here we have the results of fracture toughness distributions for all PCVN configurations, including the standard 1T SCB configuration to ID and assessing the relative change in fracture toughness. Here, the solid symbols represent the valid data, and the open symbols represent the censored data. Take a look at these curves. The black curve refers to the standard 1T SCB configuration. And here we can observe that the toughness distribution of the plane-sided PCVN with S over W equals to 4 and the toughness distribution of the plane-sided PCVN with S over W equals to 6 are both shifted to the right with regarding to the standard configuration, which provides consequently a higher characteristic toughness. And here we can observe an opposite behavior. The toughness distribution of the plane-sided PCVN with S over W equals to 8 and the toughness distribution of the side-grooved PCVN with S over W equals to 6 are both shifted to the left with regarding to the standard, to the toughness distribution of the standard geometry. And here we can also observe that this non-standard configuration provides a smaller number of censored data when we compare it to the standard PCVN configuration. From now I'm going to evaluate the reference temperature using the master curve procedure. Recalling the master curve methodology, this procedure provides a reference temperature which is defined as a temperature at which median toughness for 1T fracture specimen is equals to 100 megapascal square root meter. And here we have the master curve obtained from standard 1T SCB configuration. Since the fracture toughness test temperature is close to the reference temperature, this master curve can be considered a good description of the variation of the cleavage fracture toughness with the temperature. And here we have the master curve obtained from standard PCVN configuration. Here the reference temperature is essentially equal to the fracture toughness test temperature. But in this case, we should note that there are several numbers of sensored data. And here we have two master curves. The green master curves refers to the plane-sided PCVN with S over W equals to 6. And the yellow master curve refers to the side-grooved PCVN with S over W equals to 6. Here we can observe that the introduction of side grooves shifts the master curve to the right, which provides a higher reference temperature. And finally, here we can observe the master curve obtained from PCVN specimen with S over W equals to 8. In this case, the reference temperature is closer to the reference temperature obtained from the side-grooved PCVN configuration. And in both cases, there are a small number of sensory data, which provides a more reliable reference temperature. This summary table shows all the T0 results. And clearly, these later two results are strongly suggestive that the increased span can mitigate the constraint loss on T0 estimates often observed in standard PCVN configurations. So the conclusions of this work, the J-estimation equations can easily be implemented into standardized procedures for fracture toughness tests using non-standard band geometries. The potential effects of increased span on fracture toughness values can help to mitigate the influence of constraint loss on fracture assessments when more conservative values are desired or required. And increasing the specimen span to values of S over W equals to 8 in PCVN geometries also increases the reference temperature. And pending issues and ongoing work, 3D analysis on J and CTOG estimation procedure for non-standard band geometries, further toughness tests of pre-cracked Sharpie geometry with increased span for other ferritic materials, and 3D analysis incorporating a local approach to fracture to address the effects of increased span on toughness and fracture predictions using subsized specimens. And ongoing preliminary analysis are encouraging. That's all. Thank you all for your attention.